Welcome to the heating and cooling curve extra tutorial example question. Here we have a question where we're going to be mixing a 3.5 kilogram piece of ice supercooled to negative 15 degrees C with 750 grams of steam superheated at 125 degrees C in an isolated system. The question here is, what is the final temperature? In order to be able to do this, let's start by drawing a heating cooling curve where on the vertical axis we have temperature in degrees Celsius, and on the horizontal axis we have energy in joules. We start at negative 15 degrees Celsius with the ice, and we know that as it meets the steam it will rise in temperature as it gets heated up. Once it reaches 0 degrees C, however, it starts to melt, and as it melts it remains at 0 degrees C. And once all the ice is melted, it will start to rise in temperature as a liquid, eventually reaching a final temperature here, which we're going to call T subscript F. And that's the temperature that we're actually going to be looking for. If we start at the steam side of things, we know that it starts at 125 degrees Celsius. And as it meets the ice, it will start to cool. Once it reaches 100 degrees Celsius, however, it will start to condense. And as it condenses, it remains at 100 degrees Celsius until all the steam is condensed into liquid form, at which point then it can also drop in temperature. Another way to look at it is to look at a diagram over here whereby you start with a cube of ice, and we know that it heats up and remains a cube of ice at 0 degrees Celsius. Once at 0 degrees Celsius, it will start to melt, becoming liquid, again remaining at 0 degrees Celsius. And as it is heated further, it will become part of a larger amount of liquid that is partially from the ice and partially from the steam. Speaking of the steam, let's take a look at what happens to the steam over here. We have steam at 125 degrees Celsius. As it meets the ice, it will start to cool down and become steam at 100 degrees Celsius. Once at 100 degrees Celsius, the steam begins to condense and eventually forms liquid, also at 100 degrees Celsius. Once all the steam is condensed to liquid form, then it is allowed to drop in temperature, again to this final temperature that we're looking for. Okay, so some of the mathematical equations we need to look at. First of all, let's look at the idea of heat. Heat is just the transfer of energy, much like work is the transfer of energy, but heat in this case is the transfer of thermal energy, and just like work, it can be positive or negative depending on whether heat is brought into the system or brought out of the system. In this case, whether the ice is heating up by bringing heat in, or whether the steam is cooling down by taking energy out. In addition to that, the amount of heat used to heat up any material can be calculated by the product of the mass of the object or substance times the heat capacity of that material times the change in temperature. Again, just a reminder, the change in temperature is always the final temperature minus the initial temperature. In addition to this, we have heats associated with latent heats. In this case, for example, the latent heat of fusion or melting, and also we have heats associated with the latent heat of vaporization or condensation. Now, if we take a look at, back to the diagram, if we look at all the transitions or all the heats involved, we notice that there is one quantity of heat associated with the ice heating up, another quantity of heat associated with the melting of the ice, and of course then once it's all been melted, the water in liquid form from the ice is then heated up and rises in temperature. If we start from the steam side, we know that steam must cool down first from the 125 degrees, and then once it's at 100 degrees Celsius, then it must actually start to condense, and that requires some release of energy. Once it's fully condensed completely into liquid form and a liquid, it will actually start to drop in temperature, and there's heat associated with that. So if we take a look at all of these 1, 2, 3, 4, 5, 6 changes in energy or transfers of heat, what we could do is simply add them all up, and the expression we get for that is Q1 for the first one, which we know is a positive value as the negative 15 degrees Celsius ice heats up to 0 degrees C, plus Q2 where it actually melts, again gaining heat, plus Q3 where the ice that is now water is being heated up. All of these are gains in energy, and we're going to continue adding. Of course, we have Q4, which is the steam dropping in temperature to 100 degrees C. Now this is going to end up being a negative term because the final temperature is less than the initial temperature. Next we have Q5, which is where we have condensation of the steam. And again, this term has to be negative because it starts out with higher energy here and ends up with lower energy here. And lastly, Q6, where again the steam that now is water begins to drop in temperature. Of course, that drop in temperature is going to be lead to a negative term. All of these are losses, and so therefore negative. If we add up all the gains and add up all the losses, we know that for an isolated system, the sum must be 0. And again, this whole expression here is another form or version of the conservation of energy.